Hello everybody. So today I will show you a technique of taking protein crystal structures and making beautiful renders like this inside of Houdini. Now what are protein structures? So if you go to this website here, www.rcsp.org, you can read a lot about it. So these are crystal structures of proteins that people solve by X-ray crystallography, and so all of these data are publicly available, so you can just download these structures. And so there are a lot of programs that can open these structures. So one of them is PyMol, and if you open one of the structures, it looks like this. So every one of these proteins have a code associated with them. We call them Pdb ID. So if we go here and search for this Pdb ID called 4E5D, which happens to be the structure of a firefly luciferase, you can see this is the structures, and all of these different arrows and loops and so on have different notations, but that is not what we are focusing on here. So if you download this, you can go download files and say PDB format, and you can open it in lots of other programs, but I'm using PyMol here, and you can take a look at this. And so this is for actual scientific uses. So this can open files, and you can manipulate them and so on and so forth. But what these programs cannot do is produce beautiful renders. PyMol, for example, has preliminary renders, so it can ray trace, but you cannot position lights and so on. So getting a beautiful render is somewhat out of the question. So what I will show you today is how to take this data into Houdini. Because Houdini is very flexible, we can essentially import all of the coordinates of all of the atoms in the protein, and then we can reconstruct this kind of a representation. Well, this kind of representation inside of Houdini would be a tough ask, but we can produce a simpler representation like this. This is quite simple. Also, we can represent the volume of the protein like this, which is also quite doable inside Houdini. So I'll show you today how to do that as well. But the core of this technique lies using Python to read the protein file and create points inside Houdini. Let me explain. So here are some renders that we can produce. This is the volume stuff that I was talking about a moment ago, and here is another one. This is that loopy structure I showed, and you can do a lot with this. But to begin with, we have to get the data inside of Houdini. So let me go file new and scene view. So this is blank. Okay, so let's create a geo node, dive inside, get to the file shop, put in a Python node, and here we will write the necessary code to read all the information from the Pdb file and create points inside Houdini. So first of all, we have to read the Pdb file, and I wrote a function for this, and this is the function here. Let's hit Alt E and get a closer look. So this just reads the position information and a bunch of other information such as the atom name, the residue, the chain, and a lot of other information that are very useful to us, and makes a list out of it, and then does that for all the atoms in the Pdb file and in the protein essentially, and then returns that information. So now we will use that. We can use that information to create points. So here is how I am doing that. So essentially we have another function for creating the points, and then we are reading in that information that we got from the earlier function, and then setting up the points and all the other properties in here. So we have the functions in place, but Okay, one more thing, we cannot set the attributes without first defining them, so let's define those attributes. That takes care of that. Get rid of these two lines. And so here we have it. Now here we are reading in that PDB file that we just downloaded from the web. So if you remember, this is the E5D, and if you just go PDB format, you can download it, and this is the file that we are referencing here. Now if I hit apply and go here H, you will see that all of the points from that PDB file has come through. So this is essentially all the information or not all, but most of the information that PDB file actually contains. So let's take a look. Now let's close this and take a look at the geometry spreadsheet. So here is what I was referring to earlier, that I have, apart from the position file, position information, I have also imported quite a bit of other information, such as atom index, atom name, atom type, chain and residue number. So all of these can be used in various different ways, and that's why I have just imported them. So we will not be using all of this in this case, but you can use it in many other cases. So this is the most interesting part of this tutorial actually, because now with all of those information we can very easily create the geometry. So people who work with proteins will know that proteins have what we call a main chain, and here, because I have these atom names, I can very quickly isolate that. So what we will have to do is append a blast node, say points, and say atom name is equal to CA. So delete non-selected, and now you will see that all the atoms that has atom name with it has come through here. So these are called alpha carbons, and you will see that if I go to the geometry spreadsheet, these are all carbons. So the atom type is C, and so the main chain is built out of alpha carbons, and then we'll also have some other atoms. I'll not go into the specifics here, that's a bit unnecessary. So and also there is an oxygen, but I'll just exclude it for now, or let's put it in. It doesn't take much. So this is the actual main chain, and so now if you look here closely, you will see an interesting pattern going on. So you will have NCSCO, NCSCO, and that pattern repeats, and you notice that the residue number is incrementing. So for each pattern the residue number will increase by 1. So this in fact is one amino acid. NCSCO corresponds to one amino acid. Obviously people who work with protein will know all that. So now we have all of these atoms from the main chain, and now what we can very easily do is just connect them. So connect adjacent pieces, go here, go here, save points and set the search radius to 1, and that actually gets us pretty much the molecular structure of the entire main chain of the protein. This in itself is interesting, so you can essentially just pipe wireframe or polywire, what have you, and then render this out. That will work. But what I am after in this case is that loopy thing that I showed you here. Well, a little bit more sophisticated version of this. So this is essentially that main chain, but we do not have that carbonyl oxygen which is sticking out here. So these branches are all oxygens and they are sticking out from the main chain. So we do not need it. So let's remove it from the last here. So those are gone now, and you can see that this sort of resembles this loopy structure, or they're exactly the same thing essentially. Now what we can do is generate a curve out of this, or generate a spline out of this, but we cannot use connect adjacent pieces because this essentially gives us 1,000 or so primitives. So we need one primitive because we would like to smooth it out later on. So what we can do essentially is fuse probably. Yeah, that also does work, I think. Nope. Okay, so what we have to do is we have to use add, and we go to polygons by group, and that does it because now we have only one primitives. So this is essentially just one spline that has all those points in it, but be careful that you do not have multiple chains on this protein. This protein conveniently has only one chain, but if you had multiple chains, well, obviously you have a chain parameter, so you can just blast it out. That shouldn't be a problem. So for this demonstration I'll just stick with this, but if you had multiple chains, you will need another blast to take care of that. So now we have that very jagged looking spline. What we can do is just smooth it out. So we smooth it, and now it looks very nice and organic and loopy. So you can see that proteins have helices inside them, and you can clearly see those helices here. And now so we can just take our wireframe and put it here and whatnot, whatever you wish. That is up to you. So once you have this point information, essentially it's very easy to do the rest. I mean, that's just pretty much Houdini knowledge. You don't need anything else. Very simple. Now what would be more interesting if we could take those points that we had and create a surface. Well, in Houdini this is quite easy. So what we will do is we will create another geo for this because I don't want to mix the two up. So let's just turn that off and delete that and say object merge here, and we will select the Python node. So now our points are here again, and now what we would like to do is create a volume from this. So of course create SDF from particle, sorry, not SDF, what I'm saying, VDB from particles. So VDB from particles, append that, and we get this very crisp, very nice looking balls. But we do not really need this much resolution because we would ultimately like to create a surface. So we would end up smoothing it anyway. So so this much of resolution is not necessary. So we can just lower this down. Okay, that is a bit too much. So let's say 1.5, and this is 0.5. That pretty much works. So you can keep it higher, but that doesn't make much sense in this case. So I just go with a lower voxel size. So now we can do a VDB reshape, just to dilate this out a little bit. This is up to you if you want to do this or not. And then we will do a smooth, and that gives us this nice looking surface. Of course, as you realize, you can tweak any of these parameters to get the desired effect that you're looking for. For example, if I bump up the resolution here, no, sorry, I bumped down the resolution. So if I bump up the resolution here, then the smoothing obviously takes a little bit longer, but I get so-called, so I get a little bit more resolution out of the mesh. So let's go to something like 0.3, and this is why I am going with a lower resolution, because otherwise you will need a lot of smoothing to do this. You can choose different methods for smoothing. Let's go with this, and that looks like a nice surface to me. But this surface has no color, so how do we get this kind of color information? So remember that these are just the colors from the atoms. So red represents oxygen and blue represents nitrogen. So now in Houdini we have this information essentially. If we look at our original points, we have this atom type, and we can color the points based on this atom type, and then we will have a representation like that. So what we can do is just quickly write a wrangle to do that. So say point wrangle. And this point wrangle will take care of setting the colors up for us. Do all the brackets first. If match, because we are comparing two strings, and so our string would be, or the pattern in this case would be C, that if that matches with our attribute, which is a string called atom type. So if our atom type is C, which is a carbon, then we will give it a sort of a middle gray color. So we'll say attribute CD equals 0.5, 0.5, 0.5. Okay, what's the problem here? Okay, forgot the semicolon, as I always do, because I usually write in Python. Okay, so that takes care of that. And so now you can see that all the carbons are getting this 0.5 middle grayish color. All the others are white. So now essentially we can copy this a few times and take care of the other cases. So in a protein we have carbon, oxygen, nitrogen and sulfur. So nitrogen, oxygen and sulfur. So for nitrogen we'll give it a blue color. So let's set the B to 1. Let's leave that alone and set that to 0. For oxygen we'll obviously need a red color, so that is 1. Let's set the blue to 0 and let's leave this to be 0.25 or something. Do the same here. And sulfur is yellow, so that is 1 and 1 here. Leave this to 0. And now all of our atoms should be appropriately colored, and if you look at this point cloud, it is now much more interesting. So now but if we look at our volume, it is still black and white, of course, because this is a volume first of all. And if we, so first we will have to convert it. convert pdb, and that converts it to a polygon. So now this is a polygon, but it is still black and white. So what we can do now is transfer the attributes. So we will say attribute transfer, set that here. So from and to, and the point attributes so are already coming in, so that is there already. But look at all these jagged edges here, because the point attribute transfer transfers the attributes inside a sphere of a point, and so all of these are very jagged indeed. So what we can do is an attribute blur, and we can increase the iterations a few times. Okay, not the positions, of course, that's not going to fly, that's too much blurring. A little bit is enough actually. In this case 2 iterations seems to do the job nicely, because if you do too much, then of course you will get a very smeared result, which is not what we want. So you can see here, these are the sulfurs that are showing up in yellow here. So nice. Now it's just a matter of setting up a camera and rendering this out, which I'm not going to cover in this, but let's just very quickly do it. So we'll go up one level, create a light. Okay, so just control click here, that takes care of that, and let's just load up an environment map. We have one here, that's just an environment map, it will load in a moment. So I'll just disable the light in the viewport, and let's just create a camera here just for demonstration purposes. Go to the render view, and this is the render that I showed you earlier. And now if we hit render, it will think for a minute, and then we should get our volume, or the surface of our protein in this case. So as you can see, with minimal effort you can produce very nice results like this. And I didn't even bother creating any materials for this, but definitely you can, and that is why bringing proteins into programs like this creates very nice results like that. So that's it for this tutorial, but I would like to cover many aspects of this, because Houdini is so flexible and it allows you to access attributes in a point by point basis. So there is a lot more you can do with this, and I would explore some of that in future. For now, thank you for watching, and if you like this, please hit like and comment and let me know. Your likes and comments are very much appreciated, and this will encourage me in the future to do more videos like this. So thank you once again, and goodbye.